Oi, so that last lesson with the map mole was quite a doozy. We have a chill one right now, very, very short. This is Dropout. Specifically, what we're going to be learning today is parallel pseudo-random number generation in SRAM, right? As opposed to having to store your dropout mask on DRAM, we can keep it all in SRAM and not even store the mask itself, but just have the actual seed being stored in DRAM, and then whenever we need it, use it to create our mask in SRAM, right? So starting off as usual, importing PyTorch, Triton, Triton.language as TL, and setting our device with this weird way to grab your device that I don't know why I'm using still, but whatever, we're using it. And honestly, it's so simple. Why even bother with well, actually, no, we shouldn't. Let's do the wrapper, right? Always do the wrapper. So if we make our wrapper, this is not our kernel yet. Seeded dropout, right? We'll take as inputs an actual X tensor, a probability P, and a seed. And then we're going to pre-allocate our output, which will just be an empty tensor of the same shape and everything else as X. For a simplicity's sake, we're going to go ahead and assert that X is contiguous. I gave a lecture on contiguousness, and I believe the first or second lesson. Basically, if you do this, you don't have to worry about using the actual correct strides of X. You can assume that strides work the way you would assume strides work, with the final dimension having a stride of 1, and every earlier dimension having a stride equal to the product of what follows it. So number of elements of X is X dot numal, and we can say our launch grid is going to be a function that returns a tuple. The tuple is first entry, only entry, Triton.cdiv is going to be just, we're going to split up by our number of elements. Interesting thing here is we actually don't care what shape X is, right? Because dropout just applies the entire tensor with no real regard as to what the dimensions are. What we can actually do here is we can just parallelize in reference to the entire tensor's number of elements. So we choose a block size, make sure this right here is a tuple, and then we can go ahead and call the kernel we have not written yet, seeded dropout kernel. So I'll call it kernel, and put in our launch grid with arguments of X and the output, and then the number of elements and the probability, the seed, and we're going to go ahead and give it a block size of 1024. I know we learned how to actually get efficient block sizes in whatnot metaparameters in the last lesson, but we're going to ignore that here because we can write less code that way, and it doesn't really matter how fast this thing is actually. We're not even going to test, not even going to benchmark this one. What matters is the concept. This is not going to be a fast kernel. We're just focusing on random number generation and seeds and whatnot here, right? So then to write the actual kernel is going to be, of course, Triton.jit tells Python this is a Triton kernel, def seeded dropout kernel, and we have the pointer to the first element of our input tensor X and the pointer to the first element of our output tensor that's been pre-allocated, the number of elements in either of them, both of them, whatever, the probability, which is itself an FP32 in the range from 0 to 1, right? And a seed, which is an int32 most likely. I believe we have to have it int32 for Triton here, although I'm not sure. We'll see in a second. And block size is a constant expression known at compile time, right? So we go on our PID. PID doesn't really care about how big or what the shape of the tensor actually is. TL.program ID axis equals 0. And we're going to say our offsets are just our PID times block size plus TL.arange. This should look pretty familiar by now. 0 to block size, right? Then we can load our data from X, but first we need a mask to ensure, or just in case our block size is not a clean divisor of the number of elements. We need a mask to ensure we don't go over and read off anything that shouldn't be read off from memory that is outside tensor x's actual memory allocation. And so we say mask equals offsets less than n elements. That will only really matter and trigger for the final PID. Then we say x equals TL dot load x pointer plus offsets, mask equals mask, all boring so far. Then here is the actual lesson parts, is we can grab or create an array we call random of TL dot, excuse the chicken in the background, that's kind of odd, I don't know if you can hear that, TL dot rand using our seed, and we use offsets. So we're saying with offsets, give us random values from 0 to 1 of the shape of offsets, right? Yeah, so rand is a uniform distribution from 0 to 1. If we had done rand n, that'd be a normal distribution, and rand int is an option as well. You can check the actual documentation for all the other options. But now we have an array of length block size full of random numbers between 0 and 1, right? What we can do is we can say x keep is a mask of what values you want to keep and what we want to drop out equals random greater than p, the actual p value, right, of our dropout. And then output is going to be equal to tl.where. So this tl.where allows you to use a mask to change the values of a tensor selectively based on said mask. And the mask is going to be x keep. And so where x keep is true, we're going to put down x, and where it's false, we're going to put down 0.0. Actually, I lied. Of course, with dropout, you don't actually put the raw value of x in there. You have to, at least if you care about the distribution of the outputs not being different from when you're not using dropout, then you actually have to account for the distribution change with a divide by 1 minus p. I'm not going to go into that there in the foundations of dropout or anything, but don't forget to do that if you're writing a kernel. And tl.store, we're going to write all this back to DRAM. Output pointer, that first entry of our output tensor, and then plus our offsets to put us onto the correct subset of that output tensor. And we're going to write the output block to it, and along with, of course, a mask to prevent any writing over the edge of past the actual output tensor, right? We can use the same mask as earlier. And that was all pretty simple. We're going to also stick pretty simple for the actual test and not even do a full test, honestly. Let's just throw some values out there. Torch.random normal distribution, size of, let's say, just 8 entries, doesn't really matter. And device equals device. And then we can go ahead and say output 1 is seeded dropout x, p equals 0.5, and seed equals 1, 2, 3. And then we can do the exact same thing again. So same seed, but a different output should give us the exact same values. And finally, a third option, which we're going to use a different seed, should give us different values. We'll do a 3, 2, 1. And then we can go ahead and print our original input x, our output 1, output 2, output 3, and to make it a little prettier, just use an actual useful separator between each of those. And now this should allow us to just check, does our dropout work manually, visually, right? As opposed to usually we have a whole testing setup and everything. But Python, I'm gonna run that first try. What are the odds? Oh, never gonna work, never works. Looks like I didn't capitalize PID somewhere. Yeah, didn't capitalize PID right here. And then we can see we have our initial vector, and then the two that had the same seed do in fact have the same entries as 0 and the same adjustment for our divide by 1 minus p at the bottom, and then the different seed has different values for all of those. Fantastic. And I want to reiterate in case it wasn't clear. So a naive version of this algorithm, what it would have done is it would have used a seed to generate random numbers out here in the wrapper, aka like, or they're just somewhere out like in DRAM type thing. It would have done a whole separate kernel call to make a mask, and then it would have stored this mask right here, this X keep, it would have stored that in DRAM, and you would have had to input your own dropout mask into this kernel and then used it, right? And that means you're actually taking up all that DRAM space of whatever, however big X is, however big the actual input and output tensors are, you're storing an entire output tensor just for your dropout mask, right? If you want to have that for later for backward passes, for example. Whereas here, all we're actually storing on DRAM is this seed, is this number, right? It's just a single integer that can turn itself into a huge, huge array, a huge mask, right? Live on SRAM and only ever on SRAM, never storing all of that on DRAM. And that's kind of the point here, is if you have random numbers, probably tend to do this way so you don't have to store all of that. We are always looking to optimize to avoid both the reads and writes on the DRAM and SRAM of this Xkeep mask, as well as we want to avoid just storing and keeping on DRAM. I'm going to free up that space for something else, right? So that is it for today's lesson. I know it's a quick one. As always, any corrections will go down below, any elaborations as well. The next lesson, I believe, is our first time doing an actual backward pass with PyTorch, with Triton, and that one should be fun. Then the one after that is our final, I think it'll be in 2 parts though. That will be the flash attention implementation, which hopefully will be up by Friday, maybe more like Monday, we'll see. But yeah, end of video.